Welcome to the course on plasma physics and applications. Today we'll explore thermonuclear fusion a little bit more by looking at the power balance in a reactor and the conditions for the reactor to operate. In particular, we'll explore how to calculate the fusion power density, the losses in a fusion reactor, and the balance between energy production and losses. We'll derive the conditions from break-even and ignition. And finally, we will define the fusion energy gain, and we really clarify the conditions under which the energy production can be obtained from a fusion reactor. As a reminder of what we have discussed in a previous course, here I have reported the same picture we have shown with a DT reaction. The DT reaction has the largest cross-section and not too large temperatures, which means that's the one that we choose for operating the first generation of fusion reactor. Each reaction gives an energy that's the sum of the alpha particle energy of 3.5 MeV and that of the neutron at 14 MeV for a total of 17.6 MeV. We can look at the fusion power density from such reaction. And if we take a particular relative velocity V, that is a particular energy in the collision between the deuterium and tritium nuclei, we can evaluate the number of reactions per second per volume and multiply that times the energy for one reaction to get the power density that comes from the DT reactions. This is the expression given here, where we underline the fact that we have a dependence upon the velocity in the different terms, and therefore the overall result is still a function of velocity or energy. To get the fusion power density in the whole plasma, we need to integrate over the distribution of velocities of deuterium and tritium. We do that by assuming that the plasma is neutral, that is, the density of deuterium and tritium nuclei corresponds each to half of the electron density, which we will refer to as just N. We also neglect the impurities, and we neglect the effect of the alpha particle density, the density that is of the alpha particles that are produced by the fusion reactions themselves. We neglect that effect on the overall charge balance in the plasma. We therefore come up with an expression which gives us the fusion power density, now not a function of velocity or energy anymore, but it's an overall property of the plasma, which is then given by the reactivity integrated over velocity. The integration again is given by this symbol that we see here. And if we replace the electron density, we come up with a general expression that contains just the electron density, N square, the fusion reactivity for, of course, the DT fusion reaction that we considered throughout the course, and the energy provided by a single reaction, which is delta EF. Before proceeding to more complicated power balance exercises, I'd like to just do a brief numerical exercise. Here we consider the curve for the reaction rate calculated for a Maxwellian distribution, in fact for two Maxwellian distributions for both deuterium and tritium. This curve is given here, and it's expressed as a function of the temperature of the plasma. We're supposed to have plasma over 20 keV and a density of 5 times 10 to the 20 per cubic meter. So we look up at the curve that's plotted here for 20 keV. It's this line, and we consider the value that corresponds to that temperature for sigma V. That value is about 4 times 10 to the minus 22 in terms of meters to the third power per second. So the question we want to address in this simple numerical exercise is how much of a plasma, or in other words, how big a volume do we need to produce 1 gigawatt of fusion power? To calculate that, we take this value that we have just identified graphically for the sigma V for DT at 20 keV of temperature. We have said that that is about 4 times 10 to the minus 22 meter to the third per second. And we can then evaluate the volume, which is the fusion power divided by the fusion power density. We have chosen a reactor that produces 1 gigawatt of fusion power, so that's 10 to the 9 joule per second. And of course, we have to divide that by the fusion power density. That's given by the expression we have considered before. We can proceed in this numerical evaluation and put the numbers for our example. So I have replaced all the values for the expression for the fusion power density. We can now simplify the expression, at least in terms of the measurement units. And we find a final result, which is about 14 cubic meters. So to produce a gigawatt of fusion power in a plasma of about 20 kV with 5 times 10 to the 20 per cubic meter of density, we need about 14 cubic meters of plasma. That's an absolutely reasonable volume. It's not gigantic, nor is it microscopic. So this is giving us confidence that we can proceed in our balance between the power production by fusion and the losses and come up with a condition for the fusion reactor to operate. Let's start with some general considerations. In steady state, the sum of the power that we inject into the plasma from outside and that is produced and kept in the plasma must be equal to the losses. So that means that the heating of the plasma is equal to the losses from the plasma. The heating from the plasma comes from what we inject from outside and what the fusion reactions give in terms of byproducts that are kept inside the plasma, and that is the alpha particles. What kind of losses do we have? We have two kinds of losses. We can consider that the plasma is made of charged particles that are subject to acceleration. So there are radiative losses. But the plasma is also a fluid that's subject to direct losses like convection and conduction. So if I want to complete my little picture here with the overall balance, I need to consider that in the core of the plasma we have the alpha heating, P alpha, and that coming from outside we also have the input power, heating that we produce from outside and inject into the plasma. So this is now the power balance with the two kinds of losses, radiative and direct, and the two sources of heating for the plasma, again, in power from outside and the alpha particle power from the fusion reactions themselves. Let's look a little bit more in detail at the radiative losses. Radiative losses are in the form of Bremsstrahlung. This is the radiation that is produced by the acceleration of electrons in the field created by ions or by other electrons. The radiative power by Bremsstrahlung can be expressed, or at least its density, that is the power by the volume, can be expressed in terms of a simple expression proportional to the square of the density, to the square root of the temperature, and to a parameter called Z effective, which is defined here, which basically describes the average charge state of the ions in the plasma. For thermonuclear temperatures, the Bremsstrahlung radiation is in a range of X-rays, to which the plasma and the vessel that contains the plasma are mostly transparent, and that's why we consider this as a net loss. The spectrum of the radiation by Bremsstrahlung is indicated here, and we see that, for example, for 30 keV is in the range of X-rays. Having seen what the radiative losses are, we can look now at the direct losses in a fusion reactor. These are the conductive and convective losses. In fact, we can describe them in a very simple way using a single parameter called the energy confinement time, tau E, which is the characteristic time over which the energy is transported outside the plasma. If we assume equipartition of energy between the ion and electron species, meaning that each species has an average energy of 3/2 T, the volume is at the denominator in order to calculate the power density for the losses, and the expression is therefore simply given by the energy content of the plasma by the volume divided by this confinement time tau E, which is actually defined through this equality. The energy density of the plasma is simply the product of density and temperature times 3. And so it's 3nt over tau E as an overall estimate for the direct losses from the plasma. We are now ready to calculate the power balance in a fusion reactor. Let's do that by defining first a physics fusion gain. We refer to that as capital Q. That's the ratio between the fusion power and the input power. Naturally, a reactor can only work if Q is larger than 1, that is, if we gain power from the system. The frontier, that is the value of Q equal to 1, is called a break-even. So that's the situation in which fusion power and input power are identical. Let's evaluate this condition for the value of Q to be larger or equal to 1. As the sum of the input power from outside the reactor and the alpha particle power has to be equal to the losses, I can replace P in by the difference between the losses and the alpha particle power. Here I have specifically indicated the two kinds of losses, the direct losses, convection and conduction, and the Bremsstrahlung losses. Now we can replace the expressions that we have derived before in this ratio. Notice that in the expression for the total fusion power, the energy gain per reaction is the total delta EF, while in the expression for the alpha particle power, all the other terms are the same, but the energy gain per reaction is, of course, only the power carried by the alpha, delta E alpha. Let's simplify this expression a little bit. And write and tau E in front of all the other terms. I notice that the sum of the total energy output of a single reaction and the alpha particle output of a single reaction appears here. But we know that the total energy output of a single reaction is about 5 times the energy carried by the alpha. So I can write this as delta EF times 1 plus 1/5, which of course is 6/5 delta EF. I can therefore write N times tau E in a more complex way and impose that that be equal or bigger than 12 times the temperature divided by 6/5 times the reaction rate times the energy produced in a single reaction minus the Bremsstrahlung term. So this is the first expression that tells us how good the quality of the confinement needs to be at least in a situation in which we start gaining energy from a fusion reactor. That expression is a little bit complicated still, so let's simplify by observing the following. At temperatures that are significantly larger than 1 keV, that is temperatures that are of interest for our thermonuclear burn, the Bremsstrahlung term becomes very small compared to the other term. So that we can neglect it altogether and write N times tau E equal or larger than 12T divided by the usual fusion power production term. You can simplify this expression and come up with a very simple expression that is 10 times the temperature divided by sigma V times the energy of a single reaction. We can call this 1 over F of T. Having defined the function of temperature, and I'd like to underline the fact that it is depending upon temperature, which is sigma V, which itself is a function of temperature, times the energy of a reaction divided by 10 times T. We can represent this condition graphically, plotting N times tau E on the vertical axis and the temperature on the horizontal axis. the function 1 of f of t is represented by this red curve. That corresponds to the Q equals 1 situation or break-even situation. So reactors can have a hope to work in a region in green here above that line. If we take a typical value on this curve, we have about 10 to the 20 per cubic meter times a second in terms of n times tau E, and about 10 keV of temperature. So we have to do better than the combination of these two values in order to be in a region that is where the reactor can work. In actual reactors, of course, break-even must be exceeded because the efficiency of conversions of fusion power into electricity and the efficiency of conversion of electricity into plasma heating, they're both less than 100%. Let's look at the ultimate limit, which we refer to as ignition. That's the limit at which all the plasma heating is provided by the fusion alphas and no external power is needed to sustain the reactions. In a quantitative manner, we can define that as Q, which is the relation of fusion power to input power as going to infinity, or as the input power goes to 0. Let's translate this into an expression for n tau. So we have P in equals 0. That means that P alpha must be larger than the losses, which you have said that can be represented only by the direct loss term, as we can neglect Bremsstrahlung. So we can write the expression for P alpha and impose that be larger than the losses by direct losses, which are given by 3nt divided by the confinement time. So that means I can write n times tau E at ignition and impose that be larger than 12 times the temperature divided by sigma V times the energy that the alpha particles carry after a fusion reaction. We notice that that is 6 times over f of t, where f of t was the function that described break-even introduced before, which we can write as 6 times the condition for break-even in terms of n tau E. In practice, a reactor can and will work between break-even and ignition, that is between 1 and infinity for the value of the fusion gain Q. So if we look at the graph here, we have two curves. The red curve corresponds to ignition. The blue curve corresponds to break-even. And the reactor will operate in between, in this green region. If we define the fraction of alpha particle heating, that is the fraction between the heating from the alphas to the total heating of the plasma, that corresponds to about Q over Q plus 5, this expression. So if we want the alpha particle heating to dominate over the total heating, and that is a regime we refer to as the burning plasma, that is achieved for Q larger than 5. Finally, we need to look at the reality of a reactor. We have finite conversion efficiencies. And to account for those, we actually define a value of gain which is referred to as the engineering gain, Q sub E. And we define it as the ratio between the net electric power out to the net electric power in, or P out in engineering terms minus P in engineering terms divided by P in engineering terms. Now the P in engineering terms corresponds to the power that goes in the plasma divided by the efficiency, which we call eta E, or the conversion of the electrical power into the plasma heating. We also have to consider that the conversion of fusion power to electricity is not 100% efficient. Therefore, we evaluate that as follows. P out will be a finite efficiency term, eta T, times the input power plus the fusion power. So let's elaborate on this engineering Q. QE is equal to eta T times PF plus P in minus P in divided by eta E. These two terms are respectively the output power in engineering terms and the input power in engineering terms, divided by the input power in engineering terms. That is equal to the product of the two efficiencies times the total power minus the input power divided by the input power. We define an overall efficiency eta as the product of the two efficiencies so that we can simplify the expression and use the definition of the fusion capital Q, or the fusion gain, to get a final expression that relates the engineering gain to the fusion gain via, of course, the overall efficiencies of the two processes combined into a single parameter eta. We can represent this relationship in a graphic term and plot gain as a function of what we refer to as the triple product, the product of n times the confinement times the temperature. There is a value at which this gain will go to infinity that corresponds to ignition. And we can compare the two curves in a qualitative fashion, the physics fusion gain and the engineering fusion gain, which we will be significantly lower. Let's conclude with a numerical example. I take a reasonably optimistic set of values. I take 70% for the conversion efficiency of electrical power into plasma heating and 40% for the conversion efficiency of fusion power into electricity. That means the product of the two is 28%, and QE corresponds to 0.28 times the physics gain Q minus 0.72. For example, if I have an engineering Q of about 10, that corresponds to, or in fact needs, a physics gain of about 40. Vice versa, if I have a value of the physics gain that is Q equals 10, that corresponds to an engineering gain of about 2. So we have seen that we need, for a reactor to work, two conditions to be satisfied at the same time. The product n times tau E, where tau E is the confinement time and n is the density, must be of the order 10 to the 20 per cubic meter second, at least of that order, and the temperature has to be at least of about 10 keV. We have three ways to achieve these conditions, or three possible ways to achieve these conditions. First of all, we have the gravitational confinement. That's the way the stars work, like the sun. They hold the plasma together by gravitational forces. That's very impractical on Earth, of course. And we have two possibilities for a reactor. We have the possibility of magnetic confinement, which corresponds to a density of about 10 to the 20 per cubic meter. Very small amount of particles, in fact, in space there. But because the product has to be about 10 to the 20 per cubic meter times second, that means having a confinement time for the energy of about 1 second. And this confinement scheme, which will be discussed in the next lecture, of course, is based on the usage of magnetic fields to trap the particles of the plasma in a given volume. The sort of opposite approach is that of inertial confinement, where the density will be pushed to very, very large values, typically 10 to the 30, 10 to the 31st per cubic meter, which means that the confinement times can be very small, like 10 to the minus 11 seconds, yet to have a product that will make it work. This inertial confinement, again, will be discussed in the next lecture, and it's based on very small pellets that are made to implode via very large depositional power on their surface. In summary, we have seen that we can evaluate the fusion power density on a basis of plasma density and temperature using the fusion reaction rate sigma V. We can evaluate the power losses, which are dominated by direct losses, that is conductive and convective, and they are quantified by a single parameter called the confinement time, tau E. We also demonstrated that the net power production, that's what we want from fusion reactor, requires a physics fusion gain larger than 20, and that is between the break-even condition where Q equals 1 and the ignition condition where Q goes to infinity.